So we start with the first presentation by Olivier Kress about GStreamer, the state of the union for this year.
So, hi everyone. As I said, I'm Olivier Kress. I've been a GStreamer developer now for over 15 years. And I'm going to tell you a bit of what has happened in the GStreamer community in the last 2 years since we last met here. So we've had two major releases, 120, 122. Quite a lot of merge requests, as you can see. And the interesting fact, in 122, a third of the commits were in the Rust modules. So we've been investing quite a lot in Rust in the community. There's a lot of excitement there. And that's been the big happenings. One of the kind of big things for us as developers that we did was to merge all of the various Git repositories into one big giant repository. So now everything is together, except for Rust. Rust modules are all on the little corner because they're released with the GTK RS infrastructure instead of with the rest of the streamers. But that's kind of a big change for the developers, but it doesn't change much for the end user because we still release all the packages in separate tarballs, just like they do. Another thing that we did that's with infrastructure is we've improved our build system, and now we can select the elements one by one. Not just the plugins, but you can select exactly which element you want in the plugin. And then we can also link all the plugins, all the elements, all the dependencies into one giant library. This makes it actually easier to make a smaller build because we can build only exactly the functionality that you need for a specific application or a specific set of applications. Create a big library that only has the exact functions that are being used, right, and not anything else. So we did that for embedded systems mostly, so that you can have something a little smaller. Another area there's been quite a lot of excitement in GStreamer in the last couple of years is WebRTC. So as probably all of you are familiar with, WebRTC is a way to send video in low latency to and from browsers. And GStreamer has one of the most complete implementation outside of the Google implementation that's used by the browsers. We were missing one big bit, and that was the congestion control. And that's been added in the last releases. So now we have a module that is compatible with what's called Google Congestion Control, which is what Chrome and Firefox and Safari use. And this is in Rust. And to make that work, so we had the WebRTC implementation, but that did not do any of the actual encoding. That was left separate on purpose. Now we have a module in Rust plugin that will plug the encoder and the WebRTC and do the congestion control so that you can adapt the bitrate of the encoder to the encoding, and this is all automatic if you use this plugin. We also have whip and web. So these are also written in Rust. They're whip and web are a way to replace RTMP, but based on WebRTC. So it's a single request, a single HTTP request way to set up a WebRTC stream. It's mostly meant to stream to and from a server. So it's really a replacement for RTMP for low latency video transmission. Speaking of WebRTC, so WebRTC is based on RTP, and this is an area where there's also been quite a bit of development. So starting with CMT 2022-1 forward error correction, that's a system used mostly for legacy broadcast transmission, and we have the 2D forward error correction. So what does it mean, 2D? It means that we do forward error correction, which is basically you store multiple packets, then you generate a new one. And if you have any of these packets except one, then you can regenerate the missing one, right? That's what forward error correction is. Traditionally, you would do like packet 1, 2, and 3, and 4, and then you would generate a fifth packet. But losses tend to come in bursts in networks. So with 2D error correction, we have this kind of traditional version, and also a version where you do packet 1, and 5, and 10, right? So if you have a burst, you can recover more of the packets. The other thing that we've added, so GStreamer for a long time, we've had APIs to add RTP header extensions. That's a way to each packet to add a little header with something else. So for a long time we had libraries to actually write these, but we didn't have something in the system to easily plug in something to insert this header in every packet without having to write application code. So this is something that we've added, and we've added a bunch of different modules. Notable is this client to mixer audio level. This makes it possible for a sender of audio to say the volume that I'm sending is this, so that a mixer or some kind of service can select the person who speaks loudest without having to decode all of the audio. So it can know from this level who's speaking louder and just forward that one. Then color space. So this is for VP9. If you want to send HDR over VP9, we now have this RTP extension to make it work. It's compatible with Chrome again. So this is based on a Google experiment. And we have an AV1 payloader and depayloader. So this is, I think, probably the first thing where we've decided that the official implementation of a major feature is only available in Rust. So this is something that we're pretty happy about. Another thing, so H.264, H.265, they have two kinds of timestamp. Presentation timestamp, decoding timestamp. When you send RTP, normally you only send the presentation timestamp. You need to apply an algorithm to recover the decoding timestamp. We now have modules that generate that. We also support RC6051, so that's a way to synchronize streams immediately. So traditionally with RTP, you send two streams, audio, video, separate timestamps, and then sometimes later you get a packet telling you what the correspondence is. With 6051, we add the RTP header extension in every packet so that we can be synchronized from the first packet. And we've also improved our base class for video decoders a bit. So now it can recognize that there's a corruption and use that to request a retransmission. Previously, we kind of flagged the error, but we let the application do the decision. Now we've added something to the base class so that it's easy. Another big feature that was worked on is that we basically rewrote the HLS and Dash base class. So the previous one was over 10 years old and had been written largely without the specs. And even when we had the specs, HLS has changed quite a lot in the last 10 years. So now we have what we call almost a state-of-the-art implementation based on 10 years more knowledge. It's much more simple, has fewer threads, much better control on how we download things, on the buffering. We do a little bit of the parsing in there because sadly for many of these formats you have to actually parse the bit stream to handle it properly. So this is all implemented as one would do in this decade. We have quite a few things around decoding also, mostly video decoding. One thing I'm quite excited about is the subframe decoding that has been quite a few years coming. And this means that we now have the infrastructure in our base classes to start decoding a frame before you receive the entire frame. So some formats, H.264, H.265 particularly, we can split the frame in slices and from the first now you can actually start doing the decoding. We have two implementations of this. One is based on FPEG, which can do this only for H.264, and the other one is for the Xilinx hardware because they have the hardware features to do that. So they can do super low latency decoding. We have WebM Alpha. So the WebM format, so VP8, VP9 don't have support for transparency built in, but there's a WebM extension where we basically store two separate video streams. One with the colors and one with the transparency. And now we have an element that will spin up two decoders and then recombine them into a YUV stream. We have a DirectX 11 library, so to make it easier to integrate direct 3D 11 applications and GStreamer to do zero copy encoding for example, from a Windows application. And also, speaking of Windows, our Direct 3D 11 decoders are now the default, so the recommended choice that will get auto-plugged if you have them. So you get hardware accelerated decoding on Windows that works. Yep.
What about MacBooks, which have been more popular?
Yes, there's also
Repeat the question, Olivier.
yeah, about MacBooks.
Sorry,
what we have. So we have a hardware decoder for Mac and iOS, which is the same API.
Sorry.
CUDA, so some people use proprietary software and proprietary drivers. So we have now also a CUDA library so that you can, insert more easily CUDA data into GStreamer for encoding, streaming, decoding, all of these things. We have some more CUDA native elements. One that is a converter and a scaler, so using CUDA itself. We have CUDA and Direct 3D integration for Windows again. And this whole thing basically gives you zero copy encoding on NVIDIA hardware, especially when you match with some other CUDA-based software. But some people prefer free software. So we also have VAPI. We have a new plugin for VAPI. So we've had GStreamer VAPI for a long, long time. It was getting quite tricky. It was not based on any of the base classes that we have improved since then. So it's been completely rewritten from scratch with a new plugin that we call VA. It supports all the major codecs now. We've implemented all the ones with VA. Supports AV1, supports 5, AV8, AV9, MPEG-2. Encoding, we only have the H.264.5 codecs for now, but the rest are being worked on as we speak. And using libVA, we have a bit more VAPI. We have a bit more features. We have a compositor, so that's an element that will take 2 or more streams and composite them into the same video. We have a deinterlacer, and we have a post-processor element to do scaling and color space conversion using the video functionalities instead of the GPU. And a lot of work has happened around AV1 also in the last 2 years. So we have quite a lot now. We have support for AV1 both in the legacy VA plugin and in the new VA plugin. We have it for AMD decoders. We have it for Direct 3D on Windows using the NVIDIA APIs. For Intel using their multiple libraries, either QuickSync, QSV, or the NVIDIA SDK. So we have pretty comprehensive AV1 support in addition to the RTP plugin that I mentioned earlier. Another new thing that we've done is this is our first official machine learning integration that is in GStreamer itself. So it's a first step. And we've written a plugin to use the Onyx runtime from Microsoft to basically take some video frames, some 3D some model, and recognize objects, put little boxes in the metadata, and then another element that can take these boxes and draw them on the image. So this is the first step. A lot of work is happening right now to have a better video analytics framework as part of GStreamer. And it's nice. All these things are nice, but sometimes you want to have a UI, and a few features were recently added there. We have a GTK4 paintable, so that's an object, I would say, that you can use with the GTK4 to actually draw something on the screen. So now you can easily integrate GStreamer with GTK4, zero copy, playback. This one is in Rust, which is kind of cool. Qt6 also is a thing, so we have something that's very similar to what we had for Qt5, which is a QML item, so that you can integrate a GStreamer sync, the output with Qt, and draw in your Qt application. And the last one is a bit of a niche case. So we had a Wayland sync for a long time, And what this Wayland sync allows you to do is to basically take the video buffer and give it to the Wayland compositor directly without going through the toolkit, right? So you can use the 2D hardware planes of the platform. This is mostly useful on embedded. It allows you to do things like greater performance, not use the GPU on embedded systems where the GPU might be too slow to do video. Up to now, this all works fine, but you had to write low-level Wayland code, and that's non-trivial. So we've written a GTK widget that wraps that. So now you can write your application in GTK, just add the widget, and you get all of these performance benefits for free. Last but not least, in this category, we added touch event navigation. So previously we had navigation, we could send letters, we could send mouse clicks, but now we can also send touch events so that you can have elements in your pipeline that are controlled by the user, such as we have a web view, WebKit-based source. And we have some new tracers. So these are tools for developers to know actually what's going on in a pipeline live. We have a bunch of tracers already. 4 more were added. Some of them are like quite useful. Like we have one to generate buffer, to read the buffer lateness, and one to trace the queue levels. And these will output the information in a CSV file that you can then load and make nice graphs and understand like what's the live performance of your pipeline, what's going on. We have one to draw pretty pipeline snapshots. So for a long time we had a feature where we could draw a dot file to draw a picture of the pipeline, but this added some code to your application to actually trigger it. With this tracer, now you can just listen to a Unix signal and trigger it on the spot. The last one is the factories tracer. This is really the very first feature that I mentioned. So it's nice to say, oh, I'm going to build a GStreamer built specifically for my application with only the elements I use. But if you use Playbin, there's a lot of automated things, and you might not know exactly which plugins you've been using. So with this tracer, we can actually trace all the plugins that get loaded, all the elements that are used, and print, when you exit your application, print the list of what was actually used.
Question about that.
Yeah.
Playbin sometimes tries to use a plugin, but discards it later because it doesn't work.
It's going to be listed in the So yeah, sorry. Playbin sometimes tries to use something, but it doesn't work because the hardware is not there or something. So in this case, the tracer will still list it. So it's every plugin that is loaded, right? When they're loaded, you call a function in it, and it says no. So this is really at the loading stage at this phase. Thank you. Any questions? Yes.
You mentioned AV1 and the RTP support in there. So did you also add the SBC extensions to that, or is it still?
I have no idea.
Okay.
Anyone knows? No. No. So RTP, AV1 extension, SVC extension, and I don't know if it's there.
So we do layers selection of the highest quality right now, but it's not. There's no API.
Now there is an external, there is a dependency descriptor RTP extension where you carry information about the SBC layers in there, which is basically based under that. And so you encode the SBC layers into one string, and then you use this external extension to carry information about what's in there and so these, and so that you can do your connection. So that's what I was going to review.
None of the RTP SBC stuff, including the VP1, which is strictly required because there's no SBC inside the stream. It's not implemented yet.
Thank you.
Can summarize.
Yes, so the question was RTP, AV1, SVC, there's an extension to actually make it really useful. It's being standardized and it's not implemented in GStreamer yet. But it will be at some point.
I forgot to mention we have an online question thing on onlinequestion.org at number 43401. So if people at home want to ask questions, it's possible. But since we don't have any questions, are there any more questions on the floor?
This one there.
Q6 does support different rendering backends like DirectX on Windows and Vulkan on Linux or something. Will the QML element in Q6 support those differences that we can directly pass the DirectX buffer to the QML element?
So does Qt6 support other backends than OpenGL? And I think the answer right now is we'll only support OpenGL.
Any more questions?
Yes.
Can you do a statically linked binary?
Can you do a statically linked binary? Yes, you can. That's kind of one of the use cases, is that we create this statically linked library, and then your application can link to it and only link the required bits. So that's kind of the part of the trick to make it a little smaller.
Yeah, I have a question. So you said that there is a congestion control in WebRTC now.
Yes.
Is it like the same feature set as in the Google's implementation?
So, yeah. So the question is about congestion control in WebRTC. Is it the same feature set as the Google implementation? As far as I know, yes, because it's basically a copy of their implementation in Rust, right? So they basically re-implement the same algorithm so that it's compatible, right? It's not, but it's pluggable, so you could write your own. So there's actually a plugin mechanism, and so the core WebRTC implementation is in C, but this one is in Rust with a separate plugin. One could write a different implementation, because there's a bunch of heuristics in there. Yeah. So there's no like perfect answer.
Thank you so much.
Any other question?
Yes.
If I have an application that does the WebRTC signaling over matrix, for example, would I benefit from switching to WebRTC sync, or would I stick with the WebRTC build?
So the question is, if you have an implementation of WebRTC that does signaling something custom, for example, other matrix, would you benefit using WebRTC sync? The answer to that is yes, because it will do all of the encoding and congestion control hooked up for you. And there's an interface actually you can implement for your own signaling. So the signaling is separate from this WebRTC sync. There's still a module that you can implement. We have one implemented for like a custom signaling mechanism where there's a server that's implemented, but you could write your own in Rust.
Last question?
No, just a comment to the question before the Qt6 direct 3D integration. There is a merge request for it. We want to test that.
So Tim says that for the Qt direct, there's a direct 3D merge request open to integrate that. That's not merged yet, but do test it at home and complain when it doesn't work.
Last question? No? Okay, thank you, Olivier.